so let's do our first lesson. So this is recording, so you guys should be able to listen to this again later if you want. Um, I want to start by talking about four main things we want to understand again today, just so that it's on the video recording. Okay, so here's our four main goals. Number one, after today's lesson, I want you to hopefully have an understanding of the different units of measurement that we have and how they work in the metric system. Two, I'm hoping that you'll understand what scientific notation means. Three, which is probably new for most of you, I want you to know more about uncertainty in measurements and the words accuracy and precision. And then final, I want you to know what significant digits are, but more than just knowing how to use them, I need you to know why they're critical in physics. Okay, so those are our learning goals for the day. So let's talk about physics. I always begin my physics classes with this slide here. I want to talk about what physics is. And in order to describe what physics is, I actually talk about something else first. Any of you guys taken chemistry before? Okay. If I were to describe what chemistry is, chemistry right here is defined as the study of matter and how it changes. Okay. Chemistry is all about chemical reactions, right? How calcium chloride reacts with lead nitrate. Right? That's chemistry. But the reason I point that out is I need you to know this word right here. I need you to know what the heck matter is. You guys know what matter is? Okay, what's matter? Okay, I mean, people sometimes know what it is. Here's a good word for it. Matter is stuff. That's a really good person word for it. Anybody know the technical definition of what makes something matter? There's two requirements for something to be matter. Go for it. Oh, you nailed it. Good job. Matter is anything that has a mass and requires space. As a counter example, you ever heard of a vacuum? A vacuum is where there's three-dimensional space and literally nothing inside of it. So like we sometimes vacuum seal our food where we suck all the air out. Space is a vacuum. In outer space, large regions of space, there is literally nothing there. There's no air, there's no atmosphere, there's no oxygen. Unless there is a planet or a rock or something going through it, there's nothing there. So it has space but not mass. Well, matter has both three-dimensional territory and it weighs something. Okay. Now, the reason why I talk about chemistry first is that helps me lead into what physics is. Physics is the relationship then between matter and energy. The stuff that we have in our universe is cool, but if it doesn't do something, if it doesn't move around, if it doesn't accomplish a task, then what's the point? This chamois that's sitting on my desk right there, it's mass, it's matter. It's kind of boring. It's not really doing anything. There's not a lot of physics happening there. But if I do this, sure, now we can talk about physics principles, air resistance, gravity. We can plot its trajectory, all because of this word, energy. So that's why we're starting our unit with energy, because energy is really the impetus behind what gets stuff going in the physics world. Okay. I like this diagram here, not because it like shows the superiority, but like physics and chemistry are really the hub upon all sciences and how they kind of work together. Most of them are an offshoot of those two. If you take Physics 30 with me, which I'm hoping you will, we do a lot of overlap with chemistry, a ton of overlap between these two sciences. And you can kind of see how, well, chemistry can lead to biology and biochemistry, and physics leads to astronomy. But yeah, these two things are really the heart of where science kind of starts. And I like this slide here because it kind of describes, again, those two things. Physics is about matter, our stuff. Energy is the thing that gets it moving. And here are some general categories that we'll study over time. We'll talk about some generic physics. Thermal physics will involve heat, laws of thermodynamics. Waves are a very, very specific physics phenomena that we normally see manifested in light and sound. If you take Physics 30, we'll eventually talk about electricity and magnetic fields, and atomic physics is one of my personal favorites. Those are like some generic categories we kind of get into. Here's another way that we sometimes break down physics in terms of like how to categorize it. If it's about the stuff we have and the energy we give it, we can talk about whether or not it's big or small, and whether or not its energy is at a high or low state. Only we don't use the word energy, we use the word speed often. Okay, let's talk about quantum mechanics. That's actually a good one to begin with. You guys ever heard of quantum physics, or anybody watch the Marvel movies? You've seen like Ant-Man and how he shrinks down to like the really tiny size. And they talk about that being quantum. Quantum is anytime the size is like small. If the size of something is infinitesimally tiny, like electrons and protons and neutrons and stuff smaller than that, we're usually in the quantum realm. And if you're talking normal-sized stuff, it means you could be in classical mechanics. Unless we talk about its energy, because really this axis right here is about the energy we give it. And the number that we compare to is right here. It's 3 times 10 to the 8. Now, 3 times 10 to the 8 has a very major significance. Anybody know what 3 times 10 to the 8 significance is? It is. It's the speed of light. And the speed of light is the fastest speed that we believe that anything has the ability to travel, essentially. And what's really cool about that is that physics seems to work differently when you add huge amounts of energy to it. We call it relativistic, or maybe you've heard the word relativity before. Relativity. And there was general and special relativity that Albert Einstein came up with back in like the 1910s, 1920s. And most of those are theories that have something to do with, well, if we traveled the speed of light, what would happen? And like, it's very cool to talk about because we can't even test it. We can barely even test quantum mechanics. The stuff that is infinitesimally small, we can't do a lot of experiments on. The stuff that is traveling the speed of light, we can't really do a lot of experiments on. So most of the times we live here, we live in classical mechanics. You know, everyday life stuff, traveling a fairly reasonable speed, but these are just kind of the cool things to get into. Fair enough? Oh, too far. Now, at its core, physics, like I said, is about energy and matter, but it's also about making quantitative observations. And that's why today we're starting with a lesson on measurement, because unlike in math, math is where you're doing calculations. Physics is one step beyond that. You're going to do some calculations, but first you have to measure something. And many times in a word problem, we just tell you, oh, the mass was 15 kilograms. Oh, the speed was 8.5 meters per second. But we always have to consider, well, where did that measurement come from? Because in a real world scenario, stuff has to get measured. That's a really important thing. Okay? If you're going to use measurements in calculations, they have to be trustworthy and reliable. And that's going to be a major part of our conversation in a few minutes here. Before I get to that, though, I need you to know that there are seven units in all of science. And that blows people's minds sometimes because they're like, Chris, there are more than 7 units. But these are actually the 7 basic units that all of science is built on. Length, mass, temperature, time, amount, which you might notice as a chemistry overlap, current, and intensity. And that's it. Those are the only 7 things in physics that we can actually measure. You're like, Chris, I don't believe you. That is not true. Right, here's that same chart again here. Well, the reason why you might not believe me is that most other units are hybrids. They're based on like putting things together. For example, you might have seen a Pascal before, or a joule, or a Newton. You ever heard of some of those units? Well, those are hybrid units. For example, a Newton is actually made of a kilogram times by a meter, divided by a second, and divided by another second. That's what makes something a Newton. Fair enough? And so all of these units that you might have heard of that are other crazy ones like voltage, or watts for power, or electrical ohms for resistance, they're all fundamentally derived from these 7 in some capacity. Now there's also some like alternate measurement types. For example, Kelvin can also be measured in Celsius. You know, Kelvin is a way of measuring temperature, hey? You ever heard that before? There's also degrees Fahrenheit. And so one of the reasons why we really try to work with the metric system is that it's very consistent. If you had to not work in meters, but work in feet and inches, and if you had to work not in kilograms, but in pounds and ounces, like that gets really confusing over time. So one of the other topics I want you to be aware of is how to use the metric system. Okay? For all the units that we just discussed, if we work on the metric system, a very standardized unit that literally everyone in the world uses, except for the US, of course, right? It's usually fairly consistent, right? And most kids know this. It's all about either multiplying or dividing by factors of 10. Okay? I will go over this more if you need in more detail, but I'm going to give you like the short version, assuming you've seen this before in your life. If you're going up the staircase and you're going to a larger unit of measurement, you need to divide. But if you're going to a smaller unit of measurement, you need to multiply. So if it's okay, let's, before I get there, here's a chart that you may even find helpful. It's on a data sheet that I'll give you in a little while, where it talks about all the different prefixes that you can have before those main units. So you can have a meter, well then you can make it a kilometer. Or you can have a gram, you can make it a megagram. Or you can have a byte. What does a byte measure? Information. Like kilobytes, terabytes, gigabytes. You ever heard of that before? Like B-Y-T-E? You could have a gigabyte of data. Anybody have gigabytes of data on their data plan? Right? And so these prefixes here, they're what tell you how much of something you have, but in larger denominations, right? So giga and tera are often used to measure bytes of data. Sometimes we measure like really small distances in terms of nanometers or picometers. Let's try an example, because I'm fairly certain you guys have done this before. Okay? If I do lose you, though, let me know, right? I'll slow down. Do you guys feel like you can convert kilograms into grams? Okay. What I usually suggest is if you're trying to figure this out, there's really two things you got to know how to do. One, you got to figure out, are you multiplying or dividing? That's it. It's either a multiply or a divide. The other thing you need to know is by what factor are you multiplying or dividing? And it really just comes down to, do you know your prefix? What is a kilo of something? 1,000, yeah. So you're either multiplying by 1,000 or you're dividing by 1,000. The question then is, if you know your prefix and what it means, which one is which? General rule of thumb. If you are going to a bigger unit of measurement, you need less of it because it's a bigger unit. If you're going to a smaller unit of measurement, you need more of it because you have a lot of small pieces, right? So if you're going from a kilogram to a gram, are you going from a bigger unit to a smaller or smaller to bigger? You're going from big to small. Is that okay with everybody? I think everyone who said that said the right thing, right? A kilogram of something is big, a gram is small. So therefore, if you want to have a lot of small little things, you should times by 1,000. So 8,000 times by 1,000 will give you 8 million. So 8,000 kilograms is 8 million grams. So far, so good? Okay, let's try the next one. Go from a meter to a centimeter. So we'll worry about the multiply divide later. What's a centi? How much is a centi? Nope, not 10. It's 100, yeah. And like if you ever get stuck, you usually get a chart like this, and you'll see that a centi is times 10 to the minus 2. 10 to the 2 is 100. We'll talk about the minus maybe at a future example. Maybe not right this second. But maybe you'll just know some of these, right? Like a centurion. A centurion was a general who had commanded 100 people. A century is 100 years. So step one, centi is 100. Okay, bigger question. Do we multiply or do we divide then? Is a meter bigger or smaller than a centimeter? It's bigger. Okay, so if we're going from big to small, we're going to need more of the small items. So times by 100, it'll give us 589 centimeters. And like most of you for questions like that are pretty good at that. Because like, well, you know that a meter is about yay big. And you know that a centimeter is about that big, right? So you can kind of picture if you have 1 meter, you need to have 100 of the little centimeters, right? Sometimes we can give you a more challenging one, like say this one here. 0.065 kmols to t-moles. Okay, so we got to look those ones up then. A k-mole comes from right here. That is 1,000. A t is a tera. A tera is 10 to the 12. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Bigger question is, how many times bigger is it? This is 10 to the 3, and that's 10 to the 12. How many times bigger is it? 10 to the 9. Because it's all about how many more 10s you have. This was multiplied by 10 3 times. This was multiplied by 10 12 times, so there's 9 more multiples of 10 in there. So if you can get that logic here, this we either need to multiply by 10 9 times, or we have to divide by 10 9 times. So the bigger question is, more of it or less? Is a kilo bigger or smaller than a tera? A kilo, although is big on the normal scale, it's not big compared to a tera. A tera is huge. So if you're going to a bigger unit of measurement, you need less of them. So the right answer here is you divide by 10 to the 9. So if anyone has a calculator nearby, what happens when you take 0.065 and you divide by 10 to the 9? Your calculator might say this, 6.5 e minus 11, Harrison? Cool. Which is a great segue then into my next topic. What the heck? What is 6.5 e minus 11? Anyone ever seen that one before? It's a great topic. It's called scientific notation. Sometimes that it's kind of ridiculous to measure them in kind of, standard way of writing them out. Like say this distance to the sun, it's massive, 149 billion. Let's not write it that big. Let's shorten it up a little bit. So hopefully you've seen this before. What you do is you try to figure out how many multiples of 10 you need to either shorten it up by or lengthen it by, I guess. Here I'm going to multiply by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 maybe, and write it as 1.49 times 10 to the 11. If I took 1.49 and times by 10 11 times, the first time I get 14.9, then I'd get 149. Oops. Then I'd get 1490. Then I'd get 14,900. Then I'd get 14,9000. Do you see how eventually I'd get back to this number? And I had to times by 10 11 times. Well, a shorthand notation for that is rather than writing times 10 to the power of, you could write it as 1.49 e 11. And the e just stands for how many multiples of 10 you require. Now that's for a big number. For a small number, we use a negative exponent. This number right here, the one with all of these zeros in front of it, we would write as 2.0 e minus 1, 2, 3, 4, 5, 6, 7, 8. And a minus exponent really means that you're dividing by 10. So if you took, I need to get some space here. If you took 2 and you divided by 10, you'd get 0.2. And if you divided by 10, you'd get 0.02. And if you divided by 10 again, you'd get 0.002. Can you see how you'd keep going on this over and over again? Well, if you did that 8 times, we use a negative exponent to indicate the number is getting smaller, basically. So going back to where we came into from this, 6.5 times 10 to the minus 11 is really the number 0.00000. Keep going for a while, 6.5. And if you took 6.5 and divided by 10, and divided by 10, and divided by 10 11 times, that's the number you get. So hopefully that's not brand new. I don't want to spend much more time on it than that. I do have a practice slide that if any of you want to do some practice on it, you could. But if it's okay by you, we'll move on. And then let me know if you're struggling on the concept. Because this is really the heart of my lesson today. We want to talk about when you're measuring the word uncertainty. Okay? And you probably understand the concept, you just haven't heard the vocabulary before. Okay? So here's the vocabulary I want to share with you. All measuring devices have what's known as a resolution. Okay? The resolution of this ruler right here is to the tenths. And the resolution of this ruler right here is to the nearest ones. Do you understand what I mean by resolution? It's the little notch markings on the side of it. Okay? This one right here, put little markings along the side like this every tenth. And this one right here, put every one. Now that's the resolution. We don't usually care about the resolution as much as we care about the precision. Precision is when you chose to round. Okay? At some point, you had to round a number. For example, right here, this top is 0.5. And the reason why is I can keep it past 2. I can keep it past 5. Right, this one right here is the 5 marker. But do I know exactly that it's halfway between 5 and 6? Like if you'd have told me 0.56. So I would say was measured to the hundredths. And that's where I chose to stop trying to write down. Whereas this one right here, but if you told me it was 4 times 5, but Schuling had the race of his life. He had an Olympic record. Cool, that's not my point. My point is this right here. Podium in this particular race was 1 full. You're like, give up. And as another example, this is actually 41 seconds. And you might say, well, why couldn't we measure? One person is 141.571. The next person is 141.572. You might ask, Chris, why don't we put them down? Why don't we find what the number was in the measurement to say, well, this person is 571, this is 572. Therefore, we know at the heart of that is actions. Decisions when you decide to stop moving. can't guarantee that anymore. Check out this one right here then, Florida. This one was not accurate and not precise. Does that make sense? This is Disneyland or Disney World. It is actually really precise. This probably has the highest precision of all the pictures I took. And the reason why is that it's really zoomed in. Right? If I were to have put a random number to this, let's say that the right answer for the Eiffel Tower was 7.532. Well, this is like saying 7.5. Not bad. This is like saying 8. Not as good, but still correct, right? Doesn't 7.532 round up to 8? Not as specific. This is like saying 2. Not even close. And this is like saying 2.103457. Not even close, and like detailed not close. You know what I mean? So hopefully I've helped illustrate the differences. I got a few more examples, but I got to move on because I got 10 minutes left here. Here's another way of kind of visualizing it. Accuracy is, are you right? So these ones up here were accurate because, well, you hit the dartboard, right? If there is a correct way of doing something, if there is a correct answer, you did it properly. This is precision, though. Precision is like very, very fine tuning. If you ever hear the term a precision instrument, it means you have the ability to measure something with like really, really, really small increments. As an example, go up to the front here. Here's a meter stick. This side right here, if I were to ask you to measure the width of your hair, I don't think this one's going to be very helpful, hey? Because like this is just, it doesn't have the resolution for us to be that precise. If you want to measure the width of your hair, you need one of those like really special calipers that like, you know, squeezes in on both sides and gives you a reading, right? Something digital might be more useful, right? And so if you can really narrow down a very, very fine focus, that's precision. But accuracy is whether you're on target. Here's another picture of an analogy I like. These are 4 gas gauges that you might see in your car. One of them is not accurate. Which one do I know for sure is not accurate? Can I ask why you picked that one for not being accurate? It's actually this one right here. This is the one that's not accurate. Why is this one not accurate? Yeah? Have a gas tank that is full of empty. How many of you even batted an eye when you saw it? Empty. That's not a proper measurement. It would be like if I used this measuring tool right here and cross out the number 10 right here and write the number 32. All of them. This one right here has the highest one. And in general, the more resolution you have, the more precise. I can't tell you on this gas gauge right here what percentage of gas it is. I'm going to guess that it's about 75. Because I think that this, and I think gas gauge is accurate. What? It's that you example here of it. There are some measure something, it'll land on a zero. Of that. because you hold significant measurement. A 2, a 2, a 1, and a 9. But if I'm not sure about the 3, right? 2 or 3 sig digs. Anybody ever had this explained to them before? Does round to 339.9 also rounds to 3, but I'm rounding to 1. That's what becomes a little ambiguous here. Awkward number. It could have been 296. And it could have been 299.7 rounded to 1. See how this number right here is really challenging as to what it was measured at. Now, I believe I have 2 minutes left here. Here's our point. These rules are so here. See how there's a 6 hidden down here? 6 is halfway, so the best answer for this is to call it 30.5. But I do know that I'm more than halfway. Out of time here. Did that make sense though, minus my 20? Numbers, because you have no idea what these values are, you got to cut it off. What you're probably most familiar with though is the multiplying and dividing rules. If you were to take 3.8 time here, 558. Okay, let's talk about that. This was measured and you stopped recording in the tenths. This was measured and you stopped recording in the tenths, and now you have an answer that's to the hundredths. Can you guarantee this is an 8? No. I mean, you couldn't guarantee what the next number was after this. You can't guarantee that. So the rules that you probably have learned for sig digs up till here is that this had 2 digits, this had 3 digits. You always keep the least number of significant digits. So a lot of kids say 55.48, isn't it better to write more values? And actually the truth is no, it's better not to write numbers that may not be correct. I would round this to 55 centimeters squared. Okay, I'm basically out of time for the day here because the bell's going any second. Here's what I'd love for you guys to do. Okay, that's it for my left. I'd love to write some reflections about what we talked about. Those were the 4 main topics. Share with me what you feel like you understood about that. And number 2, if you click on the lesson, there's 5 practice questions to try. Okay, my challenge for you, and this is a challenge because there's no mark assigned to it, you're just doing it for you. Try to do that for tomorrow. And if you don't finish it because you don't have time, don't stress over it because guess what? It's not for marks, right? So tomorrow when we begin class, I'll suggest, hey, if you didn't write the reflection, if you didn't try those practice questions, try them then. Okay. Yes? Yeah, did I show you where to find it well enough? So there's always a lesson and a reflection back to back, right? So let's just be thorough. I have 2 minutes. I'm rushing because it's the end of the class. I always give you a lesson and a reflection. So this is practice, and this is something to think about. Does that work? All right, cool. Any other questions? Okay, you guys can take off. I guess you got out a minute early. Have a great Tuesday, everybody. We will chat another time.